Now we are on to 5.2 and it says A and B. Oh, we skipped one. 5.1.3 says, will the sphere move to the left or the right? Now what happens is, you are holding this positively charged rod close to a neutral sphere. The positively charged rod is going to attract the electrons within the sphere. So the sphere is going to move to the left. (5.2) says A and B are two identical spheres mounted on insulated stands carrying charges of -4 microcoulomb and 8 microcoulomb respectively. 5.2.1 determine the number of excess electrons on sphere A. Now to calculate excess electrons, we have a specific formula that we use, and that formula is N is equal to Q over QE. So N represents the number of excess electrons. Q is going to be the charge on A, which is -4 microcoulomb. That is going to be -4 times 10 to the -6. And QE is going to be the charge of an electron, which is 1.6 times 10 to the -19. Now, since electrons are negative, you can put the minus in front, but they don't actually mark you down if you leave out the minus. However, what I need you to remember is that when you're solving for n, n is a quantity. So you cannot have a negative answer for n. Even if you do get a negative answer, leave the minus out. So this should give you 2.5 times 10 to the power 13 electrons. That is how many electrons are in excess. Now it says that the spheres are allowed to touch and are then separated. So remember what happens in electrostatics is, when we bring these charged spheres close together, they share their charges. But what exactly are they sharing? They are sharing electrons. It says, in which direction will electrons flow when the spheres are in contact with each other? Choose from A to B or B to A. And here's the thing, electrons always flow from the more negatively charged sphere to the less negatively charged sphere. Between these two, the more negatively charged sphere is A. So electrons are going to flow from A to B. (5.2.3) says, state the principle of conservation of charge in words. So I'll write it below, which is the net charge of an isolated system remains constant during any physical process. (5.2.4) says, calculate the new charge on sphere A. So when they ask you to calculate the new charge, basically that is the charge after they have been separated. So that is your Q net formula, which is Q net is equal to Q1 plus Q2 all over 2. So here we're going to substitute, and you actually allowed to rename Q1 and Q2. You can call it QA and QB if you'd like. Okay, here's our substitution. A was -4 microcoulomb, B was +8 microcoulomb. And your final answer is going to be 2 times 10 to the -6 coulombs. So not only will A have this charge, but B will also have this charge. This is the charge that they have after separation. Now we have some new information that says a third sphere C, carrying a charge of -6 microcoulomb, is now brought into contact with sphere B. Calculate the number of electrons transferred when these spheres are in contact with each other. So here's what's going to happen, right? We are bringing sphere B in contact with sphere C. So they're going to share their charges. But we need to figure out, after they share their charges, what is the new charge on each sphere? So let's start off by doing that using our Q net formula. So here I've written the formula as QB plus QC all over 2, just to show you that you can do that. You don't have to say Q1 plus Q2. You can label it according to what you're given. Now, since this was the situation after B was separated from A, the charge that we're going to use for B is what we previously calculated. That's going to be 2 times 10 to the minus 6. And we were given the charge on C as negative 6 microcoulomb. So that's going to be minus 6 times 10 to the minus 6 divided by 2, for which I get negative 2 times 10 to the minus 6 coulombs. Now we need the number of electrons transferred, and the formula that we use is N is equal to delta Q over QE. Now what does delta represent in physics? It always represents final minus initial. It represents a change in the system. Now when we take the final value, the final is after separation. So after separation, QB had a charge of negative 2 times 10 to the minus 6. Initially, before separation, QB had a charge of positive 2 times 10 to the minus 6. So this minus that I have in front, that is just from the formula. And in the denominator, the charge of an electron, negative 1.6 times 10 to the minus 19. Now putting this on your calculator, you should get 2.5 times 10 to the power 13 electrons. So that is how many electrons were transferred between B and C when they were brought into contact with each other. Okay, here is question 6. This is the last question of this paper based on electric circuits. It says a battery consists of 4 identical cells of unknown EMF, is connected to 3 resistors and a bulb as shown in the circuit diagram below. The connecting wires and the battery have a negligible resistance. Now, before we do any calculations, let's start off by understanding what's going on in the circuit. Firstly, we notice that we've got 2 switches. We have S1 and S2. And what's important about switches is that whenever a switch is opened, it causes a break in the circuit, meaning that current cannot pass through that point. So if there is any resistor next to that switch, current will not be able to flow through that resistor. So if a particular switch is open and there is a resistor next to it, while the switch is open, it's as if that resistor is not even part of the circuit. Now 6.1 asks you to define the term potential difference in words, which we know is the work done per unit charge or the energy transferred per unit charge. So either one of those are fine. I'm going to write down both for you. (6.2) says, which voltmeters will provide a non-zero reading when both switches S1 and S2 are open? Now, the position of the voltmeters are very important. When you have your voltmeter across the terminals of the battery, so whatever's in between the voltmeter, that is what it's measuring the voltage for. Here, it's on either side of the battery, so it's actually measuring the voltage for the battery. And that particular voltage always measures EMF or total voltage. Or V total. So here's the thing. EMF is the maximum voltage measured across the terminals of the battery in an open circuit. There will always be a reading on the voltmeter that is across the terminals of the battery. So even though all the switches are open, that V2 is going to have a non-zero reading. What about V1? V1 here is measuring the voltage through the resistors. But if the switches are opened, there is not going to be any current going through the resistors, therefore there will be no voltage. So V1 will not have a reading, but V2 will. So 6.2, the answer is going to be V2. Now it says both, no, actually not both, it says switch S1 is now closed. So I'm just gonna adapt my diagram so that it matches, or adjust my diagram so that it matches what they say, right? The switch is now closed. So switch S1 is closed while S2 remains open. And an extremely important thing that I've just mentioned before is that when the switch is opened, it is as if the resistor next to it is not part of the circuit. The reason being is because this causes a break in that wire. So current cannot pass through that point to go through the light bulb. So at the moment, if we follow the flow of current for the current situation that we have, remember current leaves the battery from the positive terminal. So current is going to flow and flow and flow. It's then going to go through the 6 ohm resistor. Nothing is going to happen here. It can't go past S2. So we ignore that entire wire at the moment. So current flows, it goes through R1, which means R1 is part of the series circuit at the moment. It continues flowing. It goes through R2, continues. It'll be measured at A. Then it flows through R3 and it goes back to the circuit. So just by keeping the switch S open, it removes the light bulb from the circuit currently. So currently our circuit is just a series circuit. We have all 3 resistors in series with each other. And they also mentioned that the ammeter reads 2 amperes. Let's just fill that in. 6.3 says calculate the reading on the voltmeter V2. Now to calculate V2, we can use V is equal to I times R. However, we need to get R total first. Since this is purely a series circuit at the moment, to get R total, and it's always good that when you calculate a value, that you fill it in on your diagram. So let's go above to V2 and let's fill in 24 volts. Now, the next part says, both switches S1 and S2 are now closed and the ammeter reads 3 amperes. So that changes things, right? Now that both the switches are closed, so here's our switch being closed. Now that both the switches are closed, the reading on the ammeter changed. So that is now 3 amperes. And the dynamics of the circuit changes because we now have the light bulb being brought back into this. So if we follow the flow of current now, what's going to happen is current is going to flow from the positive terminal. The minute current reaches this point, it's going to split up. Some of it is going to travel through R1. The rest of it is going to travel through the light bulb. That means that R1 and the light bulb are now parallel to each other. The minute the currents continue flowing and they meet up at this point, they will now recombine and they'll flow through R2. It does not split up before it flows through R2, so R2 is part of the series circuit. Okay, remember your switches were all closed. It will be measured on the ammeter, which says 3 amperes. Then it will flow through R3, which is also part of the series circuit. So what we now have is a parallel and a series circuit combined. Let's fill in what we know though. We know that in a series circuit, current is the same through all the resistors. So each resistor here for the R2 and R3 would have 3 amperes flowing through them. So 6.4.1 says they want the reading on V1. Now it's important to understand that V1 is measuring the voltage for the parallel circuit. And what we know is that V total is equal to V series plus V parallel. So what we can do is start off by getting the voltages on the series circuit, on the series resistors. And we should be able to minus those values from 24 to get V1. Now what we know about voltage in a series circuit is that it is divided among the resistors, meaning that the voltage that R2 and R3 experience will not be the same. So let's start off by getting the voltages for each one of those, R2 and then R3. Okay, so here's what I get. On resistor 2, using V is equal to I times R, where current is 3, resistance is 2, I get voltage as 6. On resistor 3, using V is equal to I times R, where current is 3, resistance is 4, I get 12. I'm now going to combine these two to get V series. So 6 volts plus 12 volts is going to give us 18 volts. Now since V1 represents V parallel, we're going to use this formula. V total is equal to V series plus V parallel. And we saw in the diagram that V total was 24. We know V series is 18. We just calculated that, and we need to solve for V parallel. We can take the 18 over to the left. It's going to subtract. We get V parallel as 6 volts. Okay, so on my diagram, I've just filled in the values that we just calculated. And 6.4.2, they want the resistance of the light bulb. So here's how we can get that. Since we know that the total current in the circuit is 3 amperes, and we know that the voltage on each resistor in parallel is the same, meaning that the light bulb has 6 volts as well as R1, we can calculate the current through R1. If we minus the current through R1 from the total current, it tells us the current going through the light bulb. And once we have the current, we can calculate the resistance. Okay, so we're going to start off by working with R1. Also notice that it is 5 marks, so the method that we use will make sense for that mark allocation. It will actually be worth the mark allocation. Okay, so here, I've started off by calculating the current through R1. Using V is equal to I times R, voltage was 6, current is unknown, resistance is 6, I get current as 1 ampere. Now, to get the current through the light bulb, so we're working with the light bulb, all I'm going to do is subtract. So I know that there is a total of 3 amperes in the circuit, which I'm going to subtract the 1 ampere. So the current through the light bulb is 2 amperes. And now that I know the current through it, I'm going to use V is equal to I times R to calculate its resistance. Where voltage is 6, current is 1, resistance is R, we can clearly see here, actually, slight mistake, current is 2, sorry, and dividing both sides by 2, R is 3 ohms. So the resistance of the light bulb is 3 ohms. If we go back to our diagram, we can fill that in, 3 ohms, and we also know the current through it was 2 amperes. The current here through R1 was 1 ampere. So it is always good that once you calculate a value, go back to your diagram and fill it in, just so that you know exactly what's going on in your circuit. Now 6.4.3, we need to calculate the energy transferred to the bulb in 1 minute. Energy transferred. Now remember your formula in grade 10 that uses energy transferred is your potential difference formula, where W is energy. But in order for us to get to that formula, we would need to get Q, because think of your formula, it's V is equal to W over Q. We're trying to solve for W currently. We know what V is, but we don't know what Q is. So we need to calculate Q first. So here's how we're going to do that. We are given time, so we can use I is equal to Q over delta T, seeing that we know current, we know time, and we should be able to solve for Q. So for the light bulb, current is 2, charge is unknown, and time was given as 1 minute, but time must always be in seconds, so 1 minute is 60 seconds. Taking the 60 and multiplying across, we get the charge as 120 coulombs. Now that we know what charge is, we can now use V is equal to W over Q. We know that the voltage through the light bulb is 6, W is our unknown, and charge is 120. We're going to take this 120 and multiply across with the 6, so we get the energy through the light bulb as 720 joules. So that is our final answer. Okay, so that actually brings us to the end of this paper. You can see that it was for a total of 100 marks.